Now this question is asked in GATE 2008. They are trying to implement a counting semaphore using Mutexes, binary semaphores. The concept is whenever we have a counting semaphore, I think you know about counting semaphore, right? You remember it, right? So counting semaphore is nothing but if it is having some positive value, that value indicates how many process can do successful down on it. And if it is having a negative value, it means that how many process have got blocked because of this counting semaphore whenever they performed unsuccessful down, right? And so now we want to implement a counting semaphore using mutexes, binary semaphores. How is it possible? The concept is like this. They are going to use two semaphores, that mutexes. One mutex will ensure that at any time only one process will ever access the counting semaphore's value, and the other mutex will ensure that whenever any process has to be blocked, it will be blocked on that queue of the mutex. I think you remember this. Even a binary semaphore will have two parts. One is the value, which is going to be 0 and 1, and other is the list, that queue, right? What does that queue contain? It contains all the set of processes which are blocked on that particular mutex, isn't it? Therefore, we are going to use two lists. See, it is now simple. I don't know how to explain it. I'll try it. You just try to understand. Now, counting semaphore has two values. In order to implement counting semaphore, you have to do two things. One thing is there is the integer which is nothing but the counting semaphore, whose value is going to represent the status of the semaphore, either positive or negative. And second is it should even contain the list which contains set of all processes which got blocked when they are trying to access the unsuccessful down on the counting semaphore. Now in order to implement this, we are going to use two mutexes. Why not one mutexes? It is not sufficient. However, two mutexes are used is, mutex means this binary semaphore. One binary semaphore is going to see that only one process will ever access the value of the counting semaphore, and in case if more than one process tries to access the counting semaphore, it will give access to only one process, and all the remaining process are going to get blocked on that particular semaphore. Therefore, one semaphore will contain, that binary semaphore will contain the set of all blocked processes which have performed a down operation while entering the while accessing the mutex. That is one thing. And second thing is the actual processes will even get blocked whenever the counting semaphore's value itself is negative. It is very difficult to explain. Okay, I'm just trying it. You just try to understand it. Once you understand, it will be very simple. See, the question is very simple, but only part is how I could convince you. How I could make you understand, that is the difficult part. Now, counting semaphore is going to have two parts. Again, see this. One part is going to be like this, an integer value. The integer value of counting semaphore indicates that if it is positive, then those many processes can enter into the critical section when they perform the down on that counting semaphore. Fine. And the second value indicates that, the second parameter required in the counting semaphore is the queue. This indicates how many, this contains the set of all processes which have performed a down operation unsuccessfully, right? Therefore, now I am going to use two mutexes, binary semaphores. One binary semaphore is responsible in order to see that not more than one process will access the integer value of this counting semaphore at the same time. The reason is, if everyone is trying to accept the semaphore value at the same time, then there will be inconsistency if you don't have any synchronization mechanisms. Therefore, one particular mutex is simply responsible for providing the mutual exclusion on the value of the semaphore. If any time more than one process tries to access that semaphore, one process will be allowed and all the other processes will be blocked, right? And later that all the other process will get chance and they will keep on accessing it whenever one process comes out of it. Therefore, one queue of the mutex is completely dedicated to the processes which got blocked for accessing the mutex value, the semaphore value, the counting semaphore value. And the second mutex is required for storing the processes which actually gets blocked when the counting semaphore value is negative. Okay, fine. So I think I know I tried my level best to explain it. If you didn't understand it, what we shall see is we shall see the code and again I'll explain you by drawing everything here. Okay, fine. So watch it now. Oral part I did it, right? I don't know whether you understood it or not. Then I'll take the code and I'll explain you. So watch it for now. They are saying that the P and V operations on counting semaphore, where S is a counting semaphore, are defined as follows. You know what is P and what is V. P means down and V means up, right? Counting semaphore, where S is the counting semaphore, right? And now P of S equal to S minus 1. So they are just defining how does this down work and how does this up work. That is what they are trying to define. They are saying that P of S equal to S minus 1. It means that if S is less than 0, then we are going to wait. Okay, see, whenever we try to perform some down, right, and what is the first thing that you do? You try to decrement the value of the counting semaphore, that you know it, right? And now if the value of the counting semaphore becomes less than 0, which means after decrementing its value by 1, if it is becoming less than 0, then what would its value be initially? Either it would be 0 or less than 0, which means it is definitely not positive, which means all the processes which are allowed to enter the critical section have already entered, right? Therefore whatever process performs a down from there on should get blocked. That is what they are doing. If S is less than 0, then wait, which means the process has to go to block state and wait, right? That is what is down. And what is up operation? Up operation is S equal to S plus 1, which means whenever any process comes out of the critical section, it is going to do S equal to S plus 1. Now if S is less than or equal to 0, what does it mean? If S is less than or equal to 0, it means that, simple, see, watch it. If S is less than or equal to 0, after incrementing its value by 1, it means that before its value is less than 0. 1 second. Now see this. After incrementing the value of S, if its value is less than or equal to 0, then what would its value be before incrementing it? Definitely it would be it would definitely be a negative value. If it is going to be less than or equal to 0 after incrementing it, definitely before incrementing it, it is going to be less than 0, which means a negative value. What does that mean? Earlier, some process is definitely blocked while performing a down operation. Therefore, we are going to wake up a process waiting on S. You know already, this is all about the counting semaphore. Now these two operations have to be realized, implemented using the operations on mutexes, right? So now we shall see how the mutexes are used. They are saying that to implement the semaphore operations P and S, right? So implement these two. To implement the semaphore operations P and S, we are doing something as follows. So one is P of S. Okay, one more thing, they are using two okay, here watch it. Assume that PB and VB are the signal operation on the binary semaphores, wait and signal operations on binary semaphores, which means PB is nothing but down on binary semaphore and VB is nothing but up on the binary semaphore. That is what they are saying. And two binary semaphores XB and YB are used to implement the semaphore operations P of S and V of S as follows, right? So now one binary semaphore is like this, watch it. Now let's see about the down operation, right? So down operation is saying that before you access S, you have to get the control over XB. Therefore, XB is going to see that at any time only one process will access the value of S. You cannot let two processes access the value of S simultaneously because there will be inconsistent values later. That is why XB is just protecting the access to S. Now, in case if after decrementing the value of S, if its value becomes less than 0, then what does it mean? After decrementing the value of S, if it is becoming less than 0, then its initial value would have been either 0 or a negative value, which means this process does not have the permission to enter the critical section, which means this process which has executed this down is supposed to get blocked. So that is why we are going to so XB, at this point the access to S is completely over, right? Here we decremented it and here we are comparing it. Access to S is completely over. Therefore, you could release S. After releasing S, you call P of YB. The reason is, once you call P of YB, right, this call is made because you are supposed to go and sleep, right? Therefore, XB is used to provide mutual exclusion on the counting semaphore, and YB is used to provide the sleep functionality. Whenever the value of S is less than 0, then you are supposed to sleep. Therefore, you are going to wait or sleep in the queue of YB. So YB contains set of all processes. The list of YB contains set of all processes which got unsuccessful down on S, right? And what about XB? XB is used for mutual exclusion on S itself, and XB list will contain set of all processes which are waiting to access S. That is the difference. S value itself has to be protected, and next thing is S functionality has to be implemented. So in order to protect the S value, we are using XB, and in order to implement the functionality of the queue of S, we are using YB. Got it? Right? And anyway, if this is not the condition, if condition is not met, then we are going to go to else, and simply we are going to release the XB. One thing you should really pay attention here is, you are not supposed to do releasing, these two statements cannot be altered. In case if you alter these two statements, what happens is, without releasing the value of X, which means without releasing X, you will go and sleep in the Y. Then what happens? No other process can ever enter the S, and everything will be deadlocked, right? These two lines are very important. What I am trying to say is, if you just alter these two lines, then what happens is, this process does not have any permission to perform a successful down on S. Therefore, it will go and sleep directly in the waiting list of YB. And now it has not released XB. Therefore, it will not let any other process get the access to S. Therefore, no other process can get the access to S. So all the process will be blocked and everything will be deadlocked. So these two order is very important, right? And anyway, if this is not met, you are supposed to release the lock on XB, so that someone else will use S, right? And now what about YB, VS? See this. Upon S means we are again going to increment the value of S, and in case if already some process are waiting on S, then we have to wake them up, right? So watch it. Now upon S, so we are going to get the access on S first. Fine. For that we are going to do down on XB, and after getting the access to S, read the value of S. If it is less than or equal to 0, then what does it mean? Earlier its value would have been negative, which means earlier some process would have been waiting. If a process would have been waiting, where would that be waiting? That would definitely be waiting in the YB, isn't it? Therefore you have to go and wake up YB. So that is why, if this is the case, we are going to wake up YB. After waking up YB, you can release the lock. You need not release the lock first. You need not release XB first and then do it, because anyway you are not going to get blocked here. But here you should release the XB, then you go for this, otherwise there will be a deadlock. Understood this? So XB is used to control the mutual exclusion on the value of S, and YB is used to store all the processes which have to be blocked whenever the value of S becomes negative, right? So now the question is, if this one has to be implemented in a correct manner, then what should be the initial values of XB and YB? Just check this, all the values. First one is saying that initial values of XB and YB are 0 and 0. If that is the case, if the initial value of XB is 0, no one can ever perform a successful down operation or up operation on S, and all the process which try to access S either by doing down or up will all get blocked and there will be a deadlock. Therefore, the value of XB can never be 0 initially. The reason is, if that is true, every process will get blocked in the waiting list of XB itself, and there will be no one to wake it up. So having XB equal to 0 is a suicide. We are not going to have it. So these two values are definitely false. I think you got the reason. And now having this XB as 1 is reasonable. So if I have XB as 1, then at least one process can access the value of this particular XB, and therefore S. Got it? So you should have XB as 1. Then what about YB? That depends. Now what is the functionality of YB? Every process which performs a down on YB, right, is supposed to get blocked right from the beginning. We are going to use YB to store all the processes which have to be blocked. So if every process has to be blocked on this, whoever does the down, initially, then its value has to be 0. In case if you initialize the value as 1, see, then what happens is, even if the value of s is negative, and when you try to do a down on this yb, then that process will successfully cross this p of s, and that process will enter the critical section. Therefore 1 and 0 is the right option. So I think some of you might have understood this. If you have understood this, you can close this video here and continue to the next video. And I'm going to extend this, and I explain you for the others. I'll try to explain this in a detailed manner, right? So you can watch it. You can continue watching it if you didn't understand till now. Otherwise, if you understood it, please close it. Fine. Now, those who didn't understand this earlier implementation, I'll take a detailed explanation, and you please watch it. So what I mean to say is, if you have a counting semaphore, you have two things. One is the value of the integer, the semaphore itself, and the other is the list, right? So the list will contain, this is the queue, right? This queue will contain set of all processes which got blocked while performing unsuccessful down on s, right? Assume that we have, initially the key s value is set to 4. Then how many processes can do the successful down operation? 4, right? And later, after 4, even if one more process comes for this down operation, that will obviously get blocked, and that will be blocked and stored in the list L, right? So now our purpose is to see that at any time only one process will access the value of s. Otherwise, what happens is, if simultaneously two processes tries to access the value of s, they both might see the value of 4, and one of them might get preempted and other will get decremented, and later if the other one comes, it will still remember that its value is 4, and again it will decrement it and store it back. Therefore it is going to lead inconsistencies, right? That is why we are going to use two semaphores. One semaphore xp, right, will have only two values, 0 or 1, right, because it is a mutex, right? And now it will have one more list. Now this list will contain set of all processes which are waiting in order to get the access to s itself, and the other one is yb. Again, this contains only two values, 0 and 1, because it is a mutex, but then this contains a list, and this list contains set of all processes which are blocked while performing down on s because the s value is negative, 0 or negative, right? You understood now? Okay, I'll just take an example. Watch it. See, now assume that p0 wants to access this perform down on s. Then it has to access this s, right? Let us say in order to access the value of s, it performed down on xb, and initially xb's value is 1. Therefore it is successful, and then it made its value as 0, and now it is accessing the value of s. While accessing the value of s without releasing xb, let us assume that p0 got preempted. Then if p1 comes and tries to access s, which means if it tries to perform a down on s, it has to access the value of s. But then already one process is still accessing the value of s, which is p0. Therefore p1 has to be blocked. P1 is blocked not because it cannot enter the critical section, it is blocked because it cannot access the value of s for some time. Got it? Therefore p1 will go and wait here, isn't it? Therefore this queue is maintained in order to put the processes which want the access to s. We don't know yet whether you have to put them there or not. Got it? And at the same time, if p2 comes and try to access s, p2 will also be kept here. p3 comes, p3 will also be kept here if they try to access this s, right? But then these processes are not blocked because the value is not available. No, these processes are blocked because they are not able to access the value of s. That's it, right? And after some time, when this accessing s is over by this particular process p0, if you let p0 run, then p0 is going to make it as 1, and therefore p0 will go out, and then p1 will try to access it, and it will now be able to p1 will be woken up, and p1 will get out of the list, and p2 will be woken up next, and p2 will get out of the list, and p3 will be woken up, p3 will get out of the list, and all these processes are going to decrement the value of s. So p0 would have decremented the value to 3, and p1 would have decremented the value to 2, and p3 would have decremented the value to, I think p0, p1, p2, yes, p3, it is p0 will see 4 and decrement it to 3, P1 will C3 and decrement it to 2, and P2 will C2 and decrement it to 1, and P3 will C1 and decrement it to 0. So finally the value of this is 0, and all this process will successfully enter the critical section. Why? Because the counting semaphore is having value of 4. Therefore P0, P1, P2, P3 are successfully in the critical section. Now assume that one more process P0, P4 came into existence. Then it will try to perform access S, and by the time all these processes have released the XB, and XB's value will be restored to 1. Therefore this process will not be blocked here. It will be successfully able to access S. And next what happens is, since the value of S is now going to be -1, right? Watch it. Now since the value of X is less than 0, then we'll try to release the value of XB, which means initially if it is made 0 by P4, it will be making it as 1, leave it, and now it will perform a down on YB. So when it performs a down on YB, it will get blocked here. Got it? Therefore the process which gets blocked inside YB, this mutex, are nothing but the process which are blocked because the value of S is negative, right? And the process which get blocked here, they are just temporarily blocking so that no more than one process will not access the value of S. Understood this? I think you understood it now, right? If you didn't understand it, please watch it over and again. The concept is simple. Now I have to implement two things here. One thing is mutual exclusion on the value of S itself, and second thing is I have to maintain two lists. One list will be the process which are accessing the S itself, and the other list will be the process which are actually depending on the value of S, right? So that is why these two semaphores are required. Got it? And now what should be the value of XB then? XB's initial value should be 1, otherwise no one will be ever able to access S. So if it's, this value is 0, then all the process will end up sitting here and there will be a deadlock. Therefore this value should be 1, right? So that at least one process will be able to access the value of S, and that process at least will get into the critical section, and later some other process can enter it. Got it? And what about this one? YB is purely used to block the process, right? Therefore this value cannot be initially 1. The reason is, if its value is initially 1, P4 will not get blocked. P4 will also happily enter into the critical section, right? Therefore this value has to be initially 0 and this value has to be initially 1. See, the concept is very simple. Once you understand it, you can answer this question in seconds. Just look at the question and understand it, right? But once you have to understand it, that is important. A beautiful question. Okay, fine. I hope that you understood it now. In case you didn't understand it, please rewind and go for it. Okay.